All right. So before I really start my talk, let's try to impress you guys who I'm at.
I can have you.
It's okay. It's okay. You just go ahead. Thank you.
Okay.
Yeah, it's fine. I can keep talking. So for those who are not very familiar with the sort of the systems here, most of the time you only see you only see a one logo equal this either this one or this one. All right. So if you sort of recall or in the next few talks, you will basically you probably will see only this logo. This is the logo of NTU, the Nanyang University, Nanyang Technological University, or you see this is a NUS. This is where we are right now here. I'm kind of like a disorder in this system, so I'm kind of holding the junk position across two universities. Okay, usually the disorder in the system is very active, but certainly I'm not the most active person in this community. Okay, so today I'm going to talk about some of our recent work happening this year, as I mentioned. It's by CVD, chemical vapor deposition method, we fabricate some, we believe it is large area single crystalline tungsten disulfide. Okay, so I understand some of us may stop by the NTU and tour our school, and the others may, due to the very tight schedule, couldn't join us. So here I would like to tour everybody here virtually to my lab. So some of us have seen this just now after the lunch in our Graphene Center. So there we have sort of a quite advanced model of a confocal Raman system, but this is not only a normal confocal Raman system. We also integrate the other two systems together with this confocal Raman system. One is the SNOM, scanning near field optical microscope. The other is the AFM. So means with this one system, we could have many options for probing of the optics, probing of the morphology force, and pick up even the near field signals. And the labs at NTU, the one this is a special one. This is customer design or requires the system. Basically, this is a magneto Raman or PL. All the Raman system can do the PL. It depends on you pick up either Raman signal or photoluminescence signal. So this one is kind of a special. So this system can go down to temperature, say 4 or 5 Kelvin. And meanwhile, we can apply the magnetic field up to 9 Tesla. And also inside this system, inside the crystal, there's 4 pieces of piezo crystal controlled states. So basically, we can do the confocal mapping of a Raman or PL down to 4 Kelvin up to 9 Tesla. And meanwhile, if you like, you can also apply the electric field. So basically, this one is just as a normal crystal, but with the optics coupling there. Okay, in one of our labs, we also have a dual beam FIB, so we can basically do some create the small features, or we can also use this one as a e-beam writer, since we have a beam blanker, so we can do the device fabrication, patterning things here. We have a few tube furnace, which is the CVD system we use for the growth of TMD, and one big first nano CVD system for growth of graphene. And also we have some facilities for the energy storage. As you can see here, we have a glove box, we have some electrochemical workstation. We have a group of, actually we have 2 groups of battery testing system. So this, of course, we have some coating system, the thin film fabrication system. As you can see here, we have one e-beam evaporator. We have some room temperature probe station for the pre-testing of the devices. Okay, so this is roughly what we have in both NTU and NUS labs here. All right, today I'm going to, like say, as I mentioned already, I'm going to talk about, mainly focus on our recent work about the tungsten disulfide. After a very brief introduction, I will move to how we prepare the so-called large-scale single crystalline monolayer tungsten disulfide, and also some of our understanding, or at least the attempts on the understanding of the optical property of this monolayer tungsten disulfide. So this slides, I got it from my postdoc. I say, can you helped me to get a slide, basically summarize the TMD. That's what I have here. Basically, the key information according to my postdoc is the H stacking, or H tab is the most stable one. And also, we are more favorable to the direct bandgap TMDs. And this turns to all the good candidates are right here. Of course, the molybdenum disulfide, tungsten disulfide, molybdenum diselenide, and tungsten diselenide are the four of them are here. Okay. To me, so far, there are two topics that are really interesting so far in the TMDs. Okay. The first one is excitonic emission. So this is very interesting for the single layer TMDs, for example, molybdenum disulfide. We always see a very strong peak. So the nature of this peak is an A-exciton, it's a trion, or it's a bi-exciton. It's kind of interesting. And also we know when we thinking this TMD layers from from monolayer to bilayer, we will lose this direct band gap, and we will have this indirect band gap. Okay. As you can tell here. And also, naturally, we'll think about if we dope the TMD single layer, or if we stretch it, we change the local temperature, or we introduce some defect, and so on and so forth, we potentially will change the light emission properties from this single layer TMDs. Another one is the pioneer and leading by Xiaodong and Yao Wang, and others, of course, like Tony. So this deal with the valley dependence. Okay, there's a valley tronics of a single layer TMD, particular molybdenum disulfide or tungsten diselenide. Okay. Let's quickly compare the most well-studied so far candidates of molybdenum disulfide and the one we are interested in our group, tungsten disulfide. So basically, they share the same lattice structure, or exactly the same, unless we change the transition metal from moly to tungsten. Okay, if you look at the band structure, they also share a lot of common things. As I mentioned already, from a thicker one to thin one, and you will see the transition of an indirect band gap to the direct band gap. And if we compare the molybdenum disulfide and the tungsten disulfide, the main difference, all to me, is the advantage of a tungsten disulfide is the stronger spin optical coupling, which gives us a more remarkable splitting of the valence band. So that's sort of a theory for studies of spin-related things. But of course, if you look at this tungsten selenide, it also have a very strong spin optical coupling, and which gives us a well-splitted valence band, okay, at the top of valence band. Whereas the band gap or the light emission of tungsten diselenide is a little bit longer in the wavelength compared to the tungsten disulfide, which is around 800 nanometer or even longer than that. So it's not really very visible. It's near the IR. So in contrast, the tungsten disulfide, the band gap is near to, for the single layer, is near to 2 EVs. So it's quite good in the sense which is visible. Okay. I really want to emphasize the difference between the molybdenum disulfide and the tungsten disulfide by using some image I just copy-paste from this company called a 2D semiconductor. So at least after just copy-paste the image. At least as some of the pictures there. This column is the molybdenum disulfide, this column is the tungsten disulfide. These are all, I believe, is a 1-to-1 ratio. So if you see, if this is the piece that we can purchase from that company, that's such small, and we compare with the molybdenum disulfide, is extremely small. And here, I did not compare with the thickness. Actually, this one is tiny, very tiny, in the sense of the dimension, or in the sense of the thickness with respect to the molybdenum disulfide. But if you look at the price, so this is a small, much smaller piece, and it's much more expensive. I guess that could be one of the possible reasons why the molybdenum disulfide is so widely studied, whereas the tungsten disulfide, not that much, yeah. There could be that, at least to me, or to my group, this is super expensive, okay? All right, so let's see who can be sort of like potentially being one who can do the very good business in the tungsten disulfide, since tungsten disulfide is so expensive. If you look at it, there's a web, serve this web of the 2D semiconductor. They are selling the monolayer tungsten disulfide by CVD. I guess also by the Scotch tape is $480 per piece. Okay, so I believe all these groups have a potential to make a very good business by selling the tungsten disulfide. So to me, the really leading or the pioneer group are the Penn State group. Okay, the early of this 2013, they published the paper in the Nanolighter for the first time to report the CVD group tungsten disulfide with the dimension of 10 to 20 micron, as you can see here. Of course, the first time report this non-uniform light emission from this single layer of tungsten disulfide. And they have their own explanation. So why the edge is bright likely is due to the termination configuration. That either is a sulfur or it's a moly. Okay? And after that work, very close in fact, so the MIT group together with a researcher from, mainly based in Taipei, so they also published their paper in this Nanolighter. They also report their result of the CVD growth tungsten disulfide. The dimension is comparable to this, so still, like say, around 10 micron. Okay? And also they observe the multiple layers there. Okay? And after that, the Penn State group report they have the ability or they are able to grow sort of a continuous multiple domain thin film or thin layer, a still monolayer of tungsten disulfide. And that's recently one is by the Professor Liu Zhongfan in Peking University. They also use the CVD to grow the monolayer tungsten disulfide. This time, the single domain is a kind of a large. It can be reached, like say, 30, 40 micron. Okay. And of course, the one, I guess this is just appear online in ACS Nano. So they report the fabrication of, again, is continuous multiple domain of a tungsten disulfide. All right. Of course, this is a company. I have no idea with the detail. If you sort of the experiment method or setup people have been using for producing the tungsten disulfide, we can see it like this. So the Penn State, they use the setup. All the setup in general is the same. It's just a normal tube furnace. And if you look at some details, so some of them use the raw material or the precursor is the oxide. It's a tungsten oxide, WO3. And the other, they use tungsten WO3 powder. And the other, they use the tungsten oxide film. They either use the ALD or use the sparking to coat a tungsten oxide thin layer or thin film first. Then they introduce they vaporize the sulfur source and to sulfurize the tungsten oxide, you eventually have the monolayer of a tungsten disulfide. Okay? And if we look at the carrier gas, the gas environment's a little bit different. Some of the groups, they just use a pure argon flowing through this tube furnace, and whereas the others use the hydrogen or even use the H2S, the hydrogen sulfur. So of course the hydrogen, we don't really want to use either hydrogen or the H2S, the hydrogen sulfur, because they're kind of either explosive, the other, this one is toxic. And also the temperature range is varying from like say 750 all the way to 950 or even 1,000 degrees. Okay. All right, let's see how we produce the large area, or say to produce the monolayer tungsten disulfide. So of course we follow the very genius strategy of a Manchester school. We use this Scotch tape to mechanically explore the single layer of tungsten disulfide. So because this is too expensive so far, so I'm the one in my group really using this one to pure off the tungsten disulfides. Okay, so it's kind of a prompt to say I'm still keep the record in my group who can really produce the large piece of the monolayer tungsten disulfide. Okay, and of course today I would like to report how we can use the the CVD, the normal tube furnace, to produce a high quality, large area of monolayer tungsten disulfide. So the tube furnace is the same. And the different things here I learned from my previous experience when I did my postdoc, grew the metal oxide nanostructures. I introduced a one-end sealed smaller inner tube inside a big quartz tube of a tube furnace. Okay, the reason is I want to have a more sulfur vapor and kind of a stable one. Okay, stable sulfur vapor. And the source we used is the same. It's a tungsten oxide powder, a very little amount of tungsten oxide spreading on the highly doped silicon with the 300 nanometer silicon dioxide. And on top, we cover another one. Okay. So for the first try, we put the sulfur just right here at the end, but still inside the tube furnace at the this upper stream side. Okay. And the temperature, the growth window for our strategy, for our technique, could be starting from 600 degrees C to 850 degrees C. So within this temperature window, we are able to produce the monolayer tungsten disulfide, but the dimension varies, different, and other property later on you will see. Okay, here we have the optical image here, which shows kind of many pieces here, but obviously we don't really have the control, but the dimension you can see, we have the size, like say 170 micron and to some, like say, tenths of a micron. And so far, the largest piece we have this perfect triangle. One is really large, let's say more than 200 micron, they cannot be a perfect triangle. You will see some distortion curve of the edge. So the largest one we have is close to 250 micron now for the single flake of a monolayer, single domain WS2 tungsten disulfide. And the AFM clearly tells us this is a single layer. As you can see, the thickness is around 0.7 nanometer. And the TEM shows the high crystal quality of the S-grain tungsten disulfide by our strategy. Okay, if we zoom in, we can see, though the edge is really sharp, if you look at it from the SEM optical and the AFM, and even the low resolution TEM, but if you really look at it closely, you see it's not perfectly atomically sharp. There's still some rough edges here. Okay, and to identify the elements of the single layer triangles, we use the TOF sims, and together with the EDEX, and it's clear we do have the tungsten and sulfur, and in this thin region, it's a monolayer region, the ratio is 1:2, and the thick one is different. And we believe this because this is kind of a transition state or intermediate state of a growth. So here we have the compounds which consist of tungsten, oxide, and sulfur. And we propose tentatively we propose a growth mechanism for this tungsten disulfide. Instead of starting the growth from nucleation, usually it's at the center, we think they start with the nucleation with many small pieces of triangles like this. Then they connect to each other when they grow big during the keep of the heating. Okay? And they consume, once you continue to supply the sulfur vapor and sulfur source, then consume these further, they being further sulfurized, then they consume this oxide compound or the mixed compound, and they thinning itself, and meanwhile they expanding, and eventually they terminate the growth when they form a perfect triangle shape here. So we sort of propose this is the one possible growth mechanism for the tungsten disulfide, okay, of course by our method. All right, let's move to the optical studies of monolayer tungsten disulfide. So first we use the Raman. One of our sort of expertise is Raman, so we use the Raman. So you can see the whole group, whole families of Raman peaks here. And the laser we use is a 532 nanometer laser, and this is sort of a resonance give us the resonance for the tungsten disulfide. That's why you see many, many strong peaks there, including some higher order overtones or the combinational mode. And of course, the most interesting two are the E2G and the A1G here. They are the good indicator of the number of layers or the thickness. Of course, here is a single layer. If you look at the cartoon of these two vibration mode, one is in-plane vibration, the other is outer plane vibrations. Okay, so the peak is so strong, so we can map up the whole. Let's say for this one is a 70, 80 micron piece of the perfect triangles by extracting the either intensity or the position of the A1G peak here. Okay, because the E2G for this laser is mixed with other peaks, so we use the A1G. And I would like to focus on this in this stuff with this slides and in the following slides. So this one, the tungsten disulfide, fabricated by our CVD, is extremely strongly emit the light. So all the image you see here and in the following slides, without any artificial treatments, we just use the normal fluorescence microscope and take the picture and paste it in the slide. So you can tell it has a very strong, extremely strong light emission. And of course, we see the non-uniformity again here. Okay, so this is basically just the fluorescence image. We want to know more details. How we can do that? We can map up this one. We record a PL spectrum from every point in this scanning range. So we extract the peak and plot the image. So we could have for example, the intensity, the PL intensity image, or we can fit the curve to have the precision or the line width of the PL, basically this peak. As we can see, this shows a very remarkable or very obvious non-uniformities. There are three dark areas, we call it bones, and the edge is extremely strong, and the position of the edge is kind of locating at a longer wavelengths. If you move from the edge towards the center, the peak will become weaker, and the position will show some blue shifts. And we have a sort of a tentative explanation or the story to explain this one. We believe all this dark area, they have more structure defect, and they cause this weakening of the peak, okay? And also the blue shift of this one, we think there's some like a charge defect which can introduce some sort of the endope, so that can shift the emission light towards the relatively higher positions. If you zoom in this area, we can see a very small sort of the big atoms peak here. This is also reasonable because since this is a monolayer, so the majority emission will be happen in the direct angle of A atoms there. Okay. All right, so as I say, we use this one and we produce the monolayer tungsten disulfide with the non-uniform light emission, but it is strong. Okay, I would like to emphasize once again. And after that, we think about whether we can do something else. We read the literature and we learn from there and say, why don't we move the sulfur outside of this one? And we heat the sulfur powder separately. The reason is if you heat a sample, if you heat a sulfur or fabricate a sample like this, we sort of do not have much control of this one because once you set the heating period, the heating parameter, you just cannot do anything. The tube furnace will become hot. Of course, the center part is the hottest, and at both sides, the upstream and downstream, the temperature will be lower. Of course, we can test this one, but we cannot control that. All right. So we move this one, then we can control that. We can start the heating of a sulfur source whenever we want, and we can stop the heating again whenever we want. So we move it outside. Actually, this strategy has been used by many groups I showed you previously. And by this way, we have sort of a better control, and we are able to produce highly uniform light emitting single layer tungsten disulfide. And if you really look at it carefully, in fact, there's still some dark lines there, but overall it's quite uniform. And meanwhile, the intensity of light emitting from this, we call it higher quality samples, is much, much stronger than this. Okay, so we compare, we put them parallel. we compare this, we call it group A, or non-uniform sample, together with this group B, which is a highly better quality and a uniform sample. You can see across the entire sample, especially from the edge to center, the group A shows a variance of intensity, as I have shown in the previous slide. Whereas for the group B, or the uniform one, across the interior of the flake, you see there's no much change. All right. So then next we compare with our S-grown tungsten disulfide, both group A, group B, and together with the Scotch tape, the molybdenum disulfide, and also we are able to grow the molybdenum disulfide single layer. Yeah, as you can see here. So we put them under the same fluorescence microscope. We set a parameter. Everything is exactly the same, and we compare the fluorescence emissions. It's quite obvious. This one gives us the strongest emission. And it's even much stronger than the molybdenum disulfide prepared by the mechanical exploration. Usually we believe this one gives us the really high quality of a single layer molybdenum disulfide. But the CVD one, you see the CVD molybdenum disulfide is weaker than this. And some researchers noticed and also mentioned, report that the CVD can be better than this, and because they believe the quality, at least the optical quality of their CVD molybdenum disulfide is better than this. That's why they observe the CVD molybdenum disulfide could even emit a stronger light than the explorated one. But for our case, anyway, there's our S-grown tungsten disulfide is much stronger than the single crystal one, the exfoliated one. Okay, so as you can also tell from here. So I would like to point out here is the log scale. So don't rate the line width here, just compare the intensity here. So this, our S-grown CVD tungsten disulfide could be 2 or 3 orders stronger than the MOS2 from the single crystal. We also studied sort of the time trace. We shine the laser and keep recording the PL emission and compare the group A, the non-uniform, with the uniform one. You see the decay of the group A and the constant response of the group B. This tells us the quality of a group B is much better than the group A, and even for the expose the sample to a strong laser beam. Okay, we try to understand of that why, again, the non-uniform sample has such a variance of light emission, and we think there's some sulfur vacancy along those dark areas, for example, the 3 backbones there, and we try to find some evidence, and here it seems we have some evidence. That's again this top seams mapping, and at the edge we have more sulfur, and in the center part we have a relatively less sulfur compound there, and we try to pick up some defect or losing of the atom in the high resolution TEM. So it also supports this story. Say in our sample, in the group A sample, there's some sulfur vacancy, kind of like a structure defect. And also we do the temperature dependent light emission of both group A and group B. You can see when we cool down to the sample local temperature, for group A is quite constant. This move to the shorter wavelengths or higher energies, whereas for the group A, they always show some variance. Okay, then that moves to the temperature dependence. So we also study the temperature. You know, this is also a kind of we learn a lot of things from graphene business. So we try to sort of study or probe the thermal conductivity of a tungsten disulfide, since it has not been studied yet. So we basically change the temperature and look at the A1G peak here, also the E2G peak here. And for this time, we use the 457 nanometer, try to avoid the resonance there. Try to clearly resolve this the E2G peak here, so we can feed the data, and by this formula, we can have the first order thermal coefficient of tungsten disulfide single layers. As you can see here, basically it's just the slope of the fitting curve here. And also we can extrapolate the omega 0, which is the zero temperature vibration of the either A1G or E2G mode. And we can suspend in that, since we have the sample we transfer to the substrate with hole, so we can have a suspended sample, and in this time, we shine the sample with various of laser powers to use the laser power to create the heat to further study the thermal conductivity, and quite typically, so we can fit our data by using this formula. Since we have the first order thermal coefficient already, so we can derive the thermal conductivity. And if we believe this group of data, this shows the tungsten disulfide is superior to the molybdenum disulfide, because the thermal conductivity from the previous literature is 1 order smaller than that. Okay. So the main theme of this workshop is beyond graphene, but it's always good for us to look the TMD behind. Okay, so actually behind the TMD, I think there's a graphene. We learned a lot of stuff from the graphene. So let me change the scale a little bit. Let's see something behind the TMD. Okay, quickly review the Raman mode of graphene. So usually we will have a very strong G and G prime or 2D in the perfect graphene single layer. If you have some defect or you focus on the edge, you will have a D or D prime. If you look at the photon dispersion, the G peak basically corresponds to 2-fold degenerate photon at the zone center here, whereas the G prime corresponds to a photon at the K point here. Okay? And the good things of a Raman for the studying of graphene or even carbon nanotube is because this G or 2D or G prime is a resonance with the electron. For example, this one is a very famous inter-valley double resonance. That's why the Raman signal of either G prime or the defect mode, they are resonance, and the signal is extremely strong. So we can easily record a Raman signal, and through the strong electron-photon coupling, we can sort of probe the electronic property or band structure of graphene. There's other modes in the a few layer graphene or graphite. This is called a C mode. Okay, as reported in this very genius paper. Okay, so the main author, I think, is somewhere in the audience. Okay, so in the bilayer, for example, you will have the shear mode. It's the rigid interlayer vibration of these 2 layers. It's called a shear mode, and that's also named by this the author of this paper called a C peak. So once you have a thicker one, the position for the C peak will change. This will deal with the restoring force when you have a thicker layer, as you can see here. Okay, if you look at the photon dispersion, this shear mode or C peak right here is around 40 Viv number. It's pretty low energy vibration mode. And if you look at the spectrum here, it's not very clear. So this is a bilayer, and this is a trilayer, and all the way to the graphite, you can see this kind of a blue shift of this C peak or the shear mode, as I mentioned previously. But this one, I believe, is very interesting and critical, because this is related or involved the entire shearing movement of the layers. So I think that could be very interesting and important for understanding of the mechanical and even electrical properties of atomically thin layer structures. So, but the problem with this shear mode, this in the graphite or a few layer graphene, is extremely weak, and it is too close to the excitation lasers. Okay, so for the normal Raman system, we always need to block the Rayleigh scattering, that is the laser lines, by using a notch filter or edge filter. And that notch filter or edge filter can almost fully block this one, and you cannot see it. But even you use a very special Rayleigh rejection component, right, to approach this one hard, and this peak is still very weak. In this paper, they use a light-doped silicon with a hole. So you have to suspend this sample, then you can observe this C peak, but it's still very weak. Okay, whether it's a possibility we can enhance this one, and we can have the possibility to deep study of this one to have a further understanding. Let's start with this. Okay, this is so-called a twisted or folded graphene. This looks like a little bit messy, too many images here. Basically, the key information here for the given excitation laser, you will have a different type of Raman photons, even they are all bilayers. Okay, Okay, it's all deal with the twisting angles. They can appear like exactly a single layer. They can appear like a bilayer, or they can appear like with an extremely strong G photon that focus on we call it a thick medium or the G resonance sample. You see the G peak can be tens of times stronger than the G prime. Okay, so what happened here actually at this lucky value of twisting angles, they will form some fine quark singularity, and that can enhance of this G peak. And if you look at this 2D peak or G prime peak of this one, it's carefully you will see this time the G prime or 2D is no longer a single symmetric peak. They will split. Okay, we explained this one. And this is not only for the happen to the 1 plus 1. If you have a folded 2 plus 2, you can also have the whole bunch, whole group of Raman patterns on the spectrum. And for the 2 plus 2, you will see the GP will also doublet splitting. We also explained this one in one of our recent work. That's due to the activation of the Raman active and the IR active mode. And for this part, my main interest is still back to this shear mode. So what happened in this so-called G resonance folded Raman of shear mode? Okay, the shear mode of this type of folded Raman. Of course, to have a shear mode, we have to have a bilayer or thicker. So this is basically a 2 plus 2. You see here, this spectrum, I'm sorry, it's a little bit smaller, but you can see this is a really low frequency wave number, low frequency Raman spectrum. This one, is, the location is near 30 wave number. You can see the G is remarkably enhanced due to the Feinhoff singularity. And meanwhile, as we expected, the shear mode is also dramatically enhanced, as you can see here. And if you change the rotation angle, the position of this shear mode doesn't change at all. So it means it's quite robust. It's just purely from the mother flake of a AB stacked bilayer, and it will not affected by the rotation or the folding. Okay, so this is 2 plus 2. What happened for the 3 plus 3? Okay, we also look at the 3 plus 3 resonance sample, as you can see here. Also, as mentioned, this is the first time we give the Raman image of a shear mode, because the shear mode is so small, even for the single spectrum, it's very hard to get it. Okay, but with this method, properly fold that, we can enhance the shear mode, we can even map up. For the 3 plus 3, so for the 3 layer, if you look at this one, so you will have one extra shear mode. Okay, this predict is very weak. It's even weaker than this. That's why in graphite, in few layer graphene, nobody really observed this one. But since you have the enhancement here, you could able to see both of the shear modes of a tri-layer graphenes here. So this is for the 3 plus 3. So if we go further crazy, if we have a 2 plus 3, what will happen? So for the 2 plus 3, the resonance is still there, the Feinhoff singularity is still there, and this time you see the combination of the shear mode of a bilayer, C2, and the other 2 shear mode from the tri-layer. Okay? Let's see whether we can even more crazy. That's it one. This is a 6 layer. Okay? So if we have a 6 plus 6, then we will have the whole bunch of a shear mode. Every one appear in this Raman spectrum. So this just tells us by properly folding this graphene layer, we are able to study every single detail of the shear mode. As a quick demonstration, so we use the temperature-dependent Raman. So we have all these peaks here, Stokes and Stokes. We fit up the position of the shear mode and also the line width. And if we use a typical one, we could have the first order, so-called first order thermal coefficient of this shear mode. But from here, we know for the suspended one or for the graphite, and we believe even for the shear mode, in addition to the thermal expansion contribution, there's also some harmonic contribution to both position and line width. This is called a multiple photon interaction. And the overall formula or the behavior can be defined by this polynomial equation. So if we use this one to fit our data, you can see the remarkable improvement of the fitting. So that tells us for this shear mode, the multiple photon harmonic interaction is dominant. And similarly, we can fit all the width of the shear mode as a function of the temperature, and we can plot the overall total effect of a phono-phono interaction and electron-phono coupling contribution. And we plot separately, we can tell actually for this shear mode, the EPC is kind of a dominant. Okay, that back to the TMD. So we also give some trial about the electronics things of our CVD growth molybdenum disulfide or tungsten disulfide. Unfortunately, so far we do not have a proper laser. You see this is blocked. Okay, but we believe if we go further, the CVD tungsten disulfide will also have a very good performance of the electronics. Okay. All right, so let me quickly summarize. So we basically use sort of a modified setup to produce the high quality, large area, single layer tungsten disulfide. Okay. So this is what we have, what I have presented previously. So we can sort of have a non-uniform the samples or highly uniform the sample. And some of us may be interested with the boundary. It's okay because this one has a very strong emission. So instead of a detailed study, you can simply use the fluorescent microscope to look at all these boundaries here. And if you think this is R, no, I can tell you. So let's see, this is the three of them. They all appear like a monolayer. If you use the AFM to study it, you can see its uniform thickness. It's all appear like a monolayer. But if you really look at the emission patterns, you can see here, this time rather than the edge is brighter, the center is brighter. Okay? And this guy, so the center is dark because it's thicker. It appears like a uniform, but if you look at carefully, there's a second boundary here, which is dark. Okay? If you look at this guy, it's even funny or interesting. There's a threefold of wheels here. Again, this image is not that clear. So this is just basically send a message to us. I'm not sure what happened exactly for the tungsten disulfide because the tungsten disulfide, the light emission is weak. It's not possible for us to really look at the pattern, the light emission pattern. But this exactly happened to the tungsten disulfide fabricated in my group. So they have a different pattern, though they all appear like a small layer. So this means we really need to be careful when we use this type of a TMD single layer for device. We have no idea whether it's uniform or not. Meanwhile, this also offer us an opportunity to really control that, to have a different properties. And if you think this is all, no, this is some more interesting thing. You see, they can show some very funny emission patterns where their thickness or the optical picture seems all like this. Everyone is the same. It's a monolayer, and they can even be like this. Okay, so with this, I think I have very important slides. Yeah, this is we propose why they appear like it because the way they form themselves, the way they grow are quite different, and then they end up with a different light emission pattern, whereas eventually they all appear like a single layer. Yeah, that's the most important slide. I would like to thank all my group members. They contribute a lot, more than I do, for whatever I have talked. Okay, thank you so much.